the test, just to see how much you have read about what's going to be on the test. How many questions will be on the exam?
30.
All right, then. So 20 it is. I made a little sample test that's down here at the very bottom, which, scrolling down to the bottom is the smart way of getting there. So these are not the questions on the exam, lest you think, ooh, I got a way to, ace this exam. I'm just going to learn what he put on that. But you have the first 10 questions are knowledge-based questions. In my education classes, we talked about, hierarchy of learning. And the very lowest level of learning is rote knowledge, like you can parrot back what the teacher told you. It's virtually worthless learning, but it is, the lowest level. And so the first 10 questions are just rote knowledge, if you know the answers. So, which is not a step in the simple 4-step scientific method discussed in class. So you read through and you say, well, pretty clearly, which one is not part of what we talked about in class? Okay, apparently pretty clearly was the wrong thing to say when I prefaced that. You never can prove something right. Right? So that was clearly not part of it. Then the next one, how many significant figures are in 123.0? Well, I'm going to have a question for you in just a minute that we'll go over that and we'll talk about it. But I put some sample questions, and I actually put a total of 10 questions up at the top that are of the same nature as the type that are on the exam. In the application, I only put one application question, but they're pretty much all one-dimensional kinematic equations, problems, and application part. And then in the synthesis, application is where you're basically repeating a problem that you've done before. And then the synthesis, which in theory would be something you haven't done. Now you've essentially done still these things, but they take a little more thought and work. The first one is a graph problem. Then we have 2 that are adding vectors, and then a couple more complicated. Well, they're not all 2-dimensional, but problems that you have to work out. Now, for these final 5, you need to draw an appropriate figure, explain the concept. The explanation does not have to be long, despite what Jordan may have told you, because he liked to write really long explanations. He teased me that he was just going to tell students that came for tutoring, just write a whole page for explanation. You can't go wrong. You can go wrong. Your explanation needs to show that you know what the concepts are and how they fit together. So in some cases, it's going to be fairly easy. In some, it's going to be more advanced. If you look at this number 16 on the graph shown below, find the acceleration. Well, how do you find the acceleration from position versus time graph? You what? Well, without calculus, you take the slope, and then that's the velocity, right? And then the slope of the velocity tells you the acceleration. So you would have to say, the slope of this, and then, plot that, and the slope of that at that point will tell me the acceleration. That would be kind of a difficult thing to do, to make the second graph and do it. So that's obviously not going to be your question. What I tried to do here was make it so it's a straight line section there. And so if it's a straight line section, then the slope of it is constant. And if the slope is constant, then it shouldn't be 0. And then here we had to add vectors. The first one is graphically. So that means you're going to do a graph. How do you add vectors graphically? Just the words, blank to blank. Okay, so you're going to show adding it tip to tail. And so I'll give everyone a piece of graph paper because it's usually easier to do your drawing on graph paper. And we may have to share because there's like protractor and ruler in the drawer here. There's supposed to be one in each drawer, but we'll have to pass it around because you need to actually make a scale. Like 1 centimeter is so much scale distance. 1 centimeter is 5 meters or whatever works with your numbers, and then measure them out at the right angle, draw them, add them together. Because I'm going to be grading on your graphing and drawing and measuring. Then the next one is exactly the same vectors. So there's no calculations or equation here. There's work, but no calculations. And so the 2 extra points will go into your figure, which is your actual work. Then for number 18, you've already drawn the figure in number 17, so you don't have to draw an additional figure, and you have to do it analytically. That's breaking into components and adding the components. So you have the same answer for both of these because it's the same problem, solving it 2 different ways. And then more difficult problems, you have to show your work and so on. No credit will be given for calculations that merely put the answer in to verify that it is correct. Right? You can't just take this and say, if I put in 8.44 seconds, sure enough, it's at the right location. Right? You have to actually do the work and solve that it's 8.44, not put in 8.44 and say, see, the test was right. Is that clear? Right? Because I don't want people to do the wrong thing and say, but I thought that's what we were supposed to do. It's the right answer, right? I gave you the right answer, so we don't have people like, I don't know if I did right. Okay, so that's what the test looks like. 20 questions. The first 2 sections, the knowledge and the application, are each worth 25% of the test grade. And then the last 5 questions, the synthesis, which are the harder ones, is worth 50% of the test grade. The test is only over chapters 1 through 3. So that means no forces on the test. So let's do some review. First, things about units. Start Sesame. Okay, come on. There we go. So what's the SI base unit for time? All of these are units of time except one. I pray that nobody answers that one here. And I know that's a challenge, but resist the urge. So to make sure people get credit as much as possible, I will read those who have not turned it in yet. So Trace, Leslie, Erika, Becky, Jeff. Oh yeah, Erika's gone, right. I skipped the other 2 that gone, but forgot about her. Yes.
Equations will be given.
Yes, the equations will be given. Actually, I didn't show you, but the page before that first question was the equation sheet. Okay, everyone, but yes, everyone. All right, so everyone said seconds. And rather than draw a card and ask somebody, what was wrong with those up there? Yeah, nothing wrong except for they're not the base unit, right? What about a parsec? That's a distance. A parsec is a parallax arc second. That's what it stands for. Okay, next question. Was the SI base unit for distance? Since a parsec we now know is distance, I put it on this one too. Battery getting low, Trace?
No, just doesn't want to accept the answer.
Well, it's probably because the battery's low. The range would drop off. Okay, Christian, Noah, Irving. See, Irving has the same issue. All right. Okay, we had one person that changed their answer from wrong to right. So meter is the standard SI unit. What's a light year? Anyone know? Not the numerical value, but what it means. The distance light will travel in 1 year. I should have known he plays the euphonium, so he's got to know his physics, right? That's the way it works. What's wrong with the kilometer?
Nothing.
Nothing. It's just a kilometer is 1,000 meters, and the meter is the standard. Right? They got that bar. That's a meter. It's the standard. Of course, it used to be the standard. Now the standard is a measurement you can make in the lab. Okay, the next one then, the base unit for mass. At least you can tell what is it I, Lord? Is it I? Okay, everyone but Cole. Okay, so this time we had some disagreement. We had 7 people that said kilogram and 19 that said gram. So, Rebecca, since we have not complete agreement,
It's gram. Or the max.
why do you say it's grams?
Because it's more basic than kilogram.
Okay. It turns out she's wrong, as was the majority here. It's kilograms. It's unique. It has a prefix for the base unit. Remember, the standard for mass is still held in a museum, and it's just the mass of this ingot, and the ingot's a kilogram ingot. So the kilogram is the base unit. That's what we use. The abbreviation MKS, M equals, of course, meter, K equals kilogram, and S equals second. There is another, let's say, substandard that has sometimes been used that is called the CGS system, and that uses centimeters, grams, and seconds. But that is not the standard. It's a different group. So those are our standard units. Okay, so that was a quick look at the units. Notice accuracy, precision, significant figures. Let's look at some significant figure type questions. How many significant figures are in the quotient? That's what you call the answer when you divide two numbers. 539.65 divided by 600. And I don't remember. Yeah, it says select all answers that could be correct. So you're going to put in like, A, B, C, D, E, F, G, H, enter. I mean, don't do that. Put the ones that you think are correct. They're not all correct, clearly. Okay, we still have quite a large group that hasn't answered. Rebecca, James, Christian, Michaela Cohen, Brandon. Still Rebecca, Michaela, Cohen. Okay, we got everybody in. 22 said 1, 6 said 2, 6 said 3, 5 said 5, and all the rest were zeros. Okay, Gila gets to weigh in on this. Which answer or answers did you choose?
I just chose A because in multiplication or division, you use the least amount of significant figures of what you're multiplying or dividing.
Okay.
If there's only one sig fig for 600, then the answer has to be 10.
Okay. If 600 has one sig fig, and so most people went with that But 600 is ambiguous. For all you know, that could be 1, or it could be 2, or it could be 3, or it could be infinite. It could be infinite because it could be a cardinal number. How many people attended? Was it 1, 2, 3, 4? If it's 600, it's exactly 600. There's no uncertainty there if you actually counted them. So there were 4 options for how significant digits you had in 600. Okay, go ahead.
Would 600 have 2 sig figs if you put it in scientific notation?
If you put it in scientific notation, you always know the number sig figs because every number in scientific notation is significant.
But as it is, it would only either have 1 or 3 depending on the decimal.
As it is, it would be 1, 2, 3, or infinite. Okay, so if you look at this, we had 6 people that said 2, 6 people that said 3. I'd be willing to bet those are the same 6 people. And we had 5 people that said 5. I'd be willing to bet that that's all but one of the people who said 6. Why? Because if you had an infinite number of significant digits in 600, then that's no longer going to be your limiting number. It's the 5 and 539.35. And so each one that had answers was a potentially correct answer. So on the test, if I were to say which ones are possible, you would need to, there are at least 2 questions that are answer multiple. And so you'd want to check all of them that could be correct.
How would that be graded? If you don't include one of them, you get the whole question wrong?
Because there are 4 correct, I'd give you 25% for each one correct, and minus 25% for each one you chose that wasn't a correct. But never going below 0 no matter how you answer. Right? So if you chose 4, 6, 7, and infinite, it would still be 0. It wouldn't be minus 1. Leslie?
So then the actual answer for this one would be A, B, C, and H?
A, B, C, and E.
Sorry.
Not H, because if 600 has infinite significant digits, then you have the least number of significant digits is the 539.35.
Oh.
All right, now let's do addition. Remember, addition, subtraction, same rule. Multiplication, division, same rule. So I just have one example of each. How many significant figures are in the sum 539.35 plus 601? It's the same numbers. Notice I took away the ambiguity. There's only one now. That there should be one. Okay, we still have the fraction's getting better suddenly. So this is another one we have to press enter to get your answer in. Trace knows he's not in yet. Noah and Brandon. Just Noah. Oh, how did you guys do in the tournament yesterday, Noah? Well, answer first. Oh, no, Noah and Brandon. Brandon's still not in. Okay, they're both in. So how'd you guys do? So, okay, I'm sorry. Okay, we won't talk about it. We had one person that said 2, 19 that said 3, 5 that said 4, 5 that said 5, 1 that said 6, 0 for the others. Okay, so we go to nice. What'd you get?
3 sig figs.
Okay, nice said 3 sig figs. Why?
6. Oh, 1.
Okay, that's not the way you do it, right? The very vast majority of students only know multiplication and division rule and don't remember the addition and subtraction rule is different. So the division subtraction rule is the greater of the least significant, I put D for digits, so sometimes LSG, sometimes, or LSF, or sometimes LSD. So the least significant digit is the smallest digit that's significant. So if we look at the number that we have, I'm happy with that color, it turns out. I'm going to go to the highlighter anyway. This 5 was the least significant digit in the first number. And the 1 was the least significant digit in the other number. Which is bigger? Okay, now the 1 is in the units place. That's what we call the ones, right? Ones, tens. The units place. And the 5 is in the hundredths. Which is bigger, units or hundredths? Units. Hence, my answer is going to be good to the units. So that means my answer is good to this digit. So how many digits starting at the left? That's right, 4. So the correct answer here was 4 significant digits. It's, like I said, it's something that is very universally forgotten by students. It's always taught, but you use multiplication division a whole lot more than you use addition, subtraction. They just forget that there's 2 rules. And so all but those 5, don't feel foolish. You are with the majority of people who forgot. Okay, chapters 2 and 3, well, to me, they're more fun sections. Chapters 2 and 3, we start doing some physics type things rather than doing math or, units, that kind of stuff. So we had to learn about vectors, scalars, coordinate systems, and how to use the kinematic equations. You will be given the kinematic equations. Like I said, if you go down to the bottom of this presentation, just before the questions I went over, you have the equation sheet you're going to have. You can look at it, you can get used to it, you can read the cartoon so you don't have to read the cartoon during the test, or you can leave it for a diversion in case you get bored or get stuck and want to do something besides work out a problem for a few minutes. So, some more questions. For a 2-dimensional coordinate system, what spatial relationship must the x and y directions have? I spell spatial wrong half the time, so I'm proud it's spelled right here. Okay. We had one person said they must be parallel, and everyone else said they must be perpendicular. So, what's the correct answer? It's good when we are pretty uniform. It's D. They have to be perpendicular so that you can uniquely define a vector by its coordinates that are perpendicular to each other. Solving problems. As you saw, there's basically 5 one-dimensional problems in the application, and then there's another 2 or 3 1 or 2-dimensional problems in the synthesis. So being able to solve problems is going to be important for around half of the credit on the test. So examine the situation before you start. Make sure you know what is going on in the problem. Make a list of what you know and what you're looking for. And notice I have here inferred in the problem. Inferred would be things like you throw the ball. It's inferred that you're throwing it on Earth where the acceleration of gravity is 9.8 meters per second squared pointing down. They don't tell you that. When they ask something like at the top of the flight, well, at the top of the flight, the speed is 0, even though they don't tell you that. So you need to be aware of those kinds of things as well, right? In physics class, we're not looking for you to be able to just reproduce or regurgitate what you've been told. We're looking for you to be able to analyze the situation. And so that's why they will leave those things as inferred, to make sure you're thinking about the situation and analyzing the situation. And not just, hey, here's an equation, I can put numbers in, and there's an answer. So make a list of what is given and what's inferred. Identify what needs to be determined in the problem, what you don't know. And then you want to find your equation or set of equations that will help you solve it. And sometimes this gets pretty tough. To think about how are things going to interrelate. I was working a problem with James before class from a physics problem website that he went to. And it has a problem where you have a projectile that is fired at an angle, and you have an inclined plane that it's going to land on, and told us the inclined plane was 10 degrees, and that it's fired at an angle of 22 degrees above that incline. And then they solved the problem with a different set of numbers because they wanted to make it fun for you, apparently, and give you the wrong answers. So in this case, you have to look, and the first thing I did was recognize, so when I break into components, what direction do I want my components to be? Blank and blank. Okay, I do use X and Y for the names of them. But directions, like if I point my fingers, what directions am I going to point them?
East and north.
Horizontal and vertical.
That's east and north.
No, east and north are both horizontal. Yes. North is like we have it that direction. East is that direction. There's north and east. But we need a vertical. Why do we need a vertical? Because I'm telling you, so you don't have to answer. Because the acceleration of gravity is in the vertical direction. We want the acceleration of gravity in just one direction. So we set up our coordinate system, and always write your coordinate system so it's clear what X is and what Y is. At this point, you're always using vertical and horizontal. But within another week, you'll do some problems where it's not vertical and horizontal. And we'll be talking about with the Y's. And then we break it into components. So if I want to break into components, what is my angle to use to break into components? 32. Because the angle between horizontal, my x-axis, and the initial velocity is that 32 degrees. And then in this case, there was something that you guys have not seen at all. What is its final height going to be? It depends on how far out it goes, right? Because you have that slope. And so you have to make an equation that says y final over x final is equal to tangent of 10 degrees. Right, here's y final. Here's x final. It's technically y final minus 0 and x final minus 0 there. It's tangent of 10 degrees because tangent is opposite over adjacent. And so that gave us one equation that nowhere have you seen. It's not in the textbook, I don't think anywhere. But the problem, I had to think it through, and I came up with that just by looking at the problem, not from anything special except for what we know about the trigonometric functions. So that's what you're going to be explaining. Whoops. I didn't write here the explanation, but here's where you put your concept in to explain. Explain your path. Explain how things fit together. So in that problem that James and I did, I would say that the final height depends on the distance traveled, the range with this relationship. So then I break into components, find the time from the horizontal motion, plug that into the vertical motion along with the equation for relating the final initial heights, and solve for the range. Right? That was probably 4 or 5 sentences. That's a fairly long explanation because it was a little involved. Then you have your equations. For each of those last 4 problems, you need to have your equations something like, okay, x equals x0 plus vx0t plus 1/2 axt squared. You need to write that out. And then you can put numbers in. But write it out first so I know, there's the equation. that they're using. Because if I just see the equation with numbers put in, sometimes it looks like you just pulled an equation out of your hat. So make sure you make it clear which equation you're starting with. And as I said before, that range equation that's in the textbook, it's not on the test, because if we have something that is a range problem, I want to see that you know how to put the ideas together, not that you can just put numbers into an equation. So it's not given if you just say, well, I memorized this equation, I put numbers into it. You don't get the full credit there, because I want to see that you understand how it works. Yeah, if you just start by writing the range equation and you don't have anything to get to that, yeah, it does you no good. Because it doesn't show being able to work a
You
problem.
don't have to use the range equation to find how far it went, do you?
Well, it depends on, you never have to use it, but sometimes you get to that equation as you're going through your derivation. Usually I have the problem so it doesn't start and end at the same height, and that way there's no temptation, right? Because that's a special use equation. It only works if they start and end at the same height. Okay, at the end, check your answers to see if it is reasonable. Make sure it makes sense. Now that reminds me, on the homework, I asked James to remind me, he forgot. It's the final problem, right, Abigail? The final problem is the one that you asked me about? Okay. The final problem, it says, find the distance below the starting height where the projectile lands and express it as a positive number. Sounds fair, right? But then they have y minus y0 equals. Well, y minus y0 is going to be a negative answer. And so you have what they wrote here is in conflict with what they tell you to write. So just pretend that they put absolute value signs there and put in a positive value for the last question, the homework that's due on, what's it, Wednesday? Yes. All right, so some practice problems. You want to throw a ball straight up in the air so it reaches a height of 3.3 meters above the ground. If the ball leaves your hand from a height of 1.2 meters above the ground, how fast do you need to throw? 1.2 meters, that's somewhere around here. That's not 3 meters. That's close to 3 meters. How do you solve it? Okay, write down the key things. So I have here a picture already so I can save myself some time. My y initial, it says 1.2 meters, so I'm going to put 1.2 meters. And it reaches a height of 3.3 meters above the ground. This picture doesn't show it from the ground, so I better put it like that. My y final equals 3.3 meters. The acceleration is already shown in the figure. I want to find Vy initial. There's one more thing I know that I did not write. Vy final is 0. How does she know Vy final is 0? Because it's at the top. What's the acceleration at the top? Negative 9.8 meters per second squared. Still accelerating downward at the top, even though the velocity is momentarily 0. So now that I have this, I look and I say, what am I looking for? I am looking for how fast it was thrown initially. So I'm looking for Vy initial equals, oh, actually I wrote it over there already. Yes, that is the way I said it. I look at this, what is conspicuously absent of variables? Time. I don't care about time, I'm not given time. That throws me straight to, I'm going to try to use the equation that's Vy final squared minus Vy initial squared equals 2ay times y final minus y initial. That has all the variables that I'm given and what I'm looking for. That should be muy bueno. So I just put in my numbers then. And actually, what am I looking for? That's not the way to solve for a v. That's the way to solve for a y. Pay attention to what you're looking for. I'm looking for Vy initial. So I am simply going to go straight to, we know that's 0. Notice I do have to be careful with my minus signs. What is AY? It's negative 9.80 meters per second squared. And then my Y final is 3.3 meters. My Y initial is 1.2 meters. Notice I have the square root of a negative times a negative. It's pretty vital, because if I have the square root of a negative number, I have an imaginary answer. Yay. Needs to be a positive inside the square root. So 3.3 minus 1.2 is 2.1. 2.1 times 9.8 is in the ballpark of 20. 20 times 2 is 40. Square root of 40 is...
Plus 6.5.
Okay, so I'm just going with Corso here. I mean, 6 squared would be 36. 7 squared would be 49. It's probably a little different, but it's in that ballpark. So, did you know?
6.32.
It's what?
6.32.
Okay, so 6.32. So take away the approximate sign. So we have that initial speed. Then the next question says, hey, what was the time? We could go back to our initial variables and say, oh, now I'm looking for time. Let's do that. Or we could say, wait, I know the acceleration, I know the initial and final speeds. There's a real simple equation that V final equals V initial plus AT. Zero point 6 what?
6.4.
6.4? 6.4 what?
It's 6.45.
6.45, okay. Since I have 3 significant digits, I'm sticking with the 3 significant. Oh, wait, no, I don't have 3 significant digits. I have only 2 digits in these numbers, so I only have 2 digits. 6.3 is the correct answer.
How much do you care on the test? For that
On the last 5, I care.
so,
It'd be 1 point if you don't have the right sig figs.
so,
Of course, you have the sig figs given already in your answer, but so it's a 6.4 or 6.5 when I round to right sig figs. Now, I did one thing that was, a technical mistake, but a practical non-mistake. Anytime you use a square root, you have 2 answers, a positive answer and a negative answer. I only put the positive answer. I said it was just a technical mistake, it's not really a mistake. Why? Because, yeah, we know it's not negative, it's not going down, it's going up. So I'm able to use my brains there to say, yeah, it's positive 6.3 because it was going up. So that's a one-dimensional kinematic equation problem. Chapter, yes, Michaela.
So on the last one, the final is 0.
Yeah.
So that's but it's saying what hits the ground. So like, are there,
Whoa, oh, it says hits the ground. I didn't see hit the ground.
yeah. So
Bueno. I was wrong, right? Because I didn't read the question. That is another thing that's really important. Read the question. I saw you talking. I didn't know what we were talking about. Yeah, got to read the question. I found the time it takes to get to the peak. Well, now what do? I go and rework it because Michaela showed that I didn't work the right problem. I worked a problem correctly, but not the right problem. So if I want to find the time when it hits the ground, what should I do now?
final is 0.
My Y final is 0. And which equation should I use? Okay, I can use the one that has, y final is equal to y initial plus vy initial t plus 1/2 ayt squared. Gives me quadratic. Put in the quadratic, gives me two answers. One's going to be negative. You know what? That's not it. One's going to be positive. That will be it. So that's one way. Another way is to go ahead and now calculate how fast it will be when it hits the ground, and then use this equation, knowing the initial speed and the final speed. Yet another way is to say, well, I've now calculated the time it takes to get to the top. Now how long is it going to take if I drop it from the top to get to the ground, and add the two times together? My parents for many years were at Mountain View College in the Philippines. That was before they were IS in the Philippines. And I went there, and their physics teacher, that was the only way he knew to solve these problems. Calculate the time it takes to get to the peak, and then calculate the time from the peak to wherever it lands, and add the two together. They had never heard of somebody that had a PhD in physics. They were baffled by my degree. Anybody know where Mountain View College is? No? It's in Mindanao. I've been there. Obviously. Okay. So what's new in chapter 4 or chapter 3? Chapter 4 is not on the test. Chapter 3, we had the addition of vectors. Make sure that you are able to do it both ways. You have the same problem. You're given the answer. You have to show how to do it both graphically and analytically. Analytically is when you're breaking each vector into its components. You add the x components together, you add the y components together to get your answer. You use the Pythagorean theorem if you want to find the magnitude at the end, which you need for the problem. And you use trigonometric functions. So let's review trigonometric functions. They will be on the equation sheet, but the ones that we use extensively in physics class are just these three. And so you don't have to have, some old hippie came a hopping through our alley. You don't have to have some mnemonic because they're given to you. I had no mnemonic for these until I became a teacher at Union College. At PUC, I'd never heard mnemonic for these either. Came here. So katoa. Okay. So those are the definitions. You need to be familiar in how to use them, how to identify the sides of a triangle. So if I give you this angle, which side is hypotenuse? Okay, the longest one. I see different answers. Some of them looked wrong, but you can't tell really. The hypotenuse is the longest one. It's opposite the right angle. Which one is the adjacent side? Okay. It's the vertical one because it's the one that is making the angle with the hypotenuse. So this is the adjacent side. And that leaves, this is the opposite side. So now that I've identified those, I can relate sides. And of course, make sure you know the inverse function, right? Inverse function of a function. Inverse tangent of theta by definition is theta. And so we use inverse tangent to go from knowing the numbers to finding the angle. Or inverse sine or inverse cosine as is your pleasure. So here's just some steps for the analytical vector addition. Select a convenient set of mutually perpendicular coordinate directions and add them to your figure. Break each vector into its components using sine and cosine. Add like components, e.g. add x components together. Use the Pythagorean theorem to find the magnitude once you found the components of your answer, and use tangent, or more specifically inverse tangent or arctangent, to find the angle of the resultant. Okay, last thing, trajectory problems. Yes, question, Brandon.
Instead of using tangent, could we not just, if we find the one angle, then we can just
I didn't understand the question.
Like, if we're solving a triangle and we get the two of the angles, we can just take the one angle and substitute.
Oh, yeah. Yes, you have your basic trigonometry. The sum of the interior angles of the triangle is 108 degrees, is what Brandon was referring to. Yeah. Okay, so a two-dimensional problem, always remember to break things into the components. So you have the x component, the y component. Make sure you identify, hey, I'm going to call the vertical direction y, the horizontal direction x. Get your initial, final, whatever variables in the x direction, in the y direction. Generally, but not always, you solve for time in the x direction, substitute it into the y, and go for it. It depends on the problem. You have to look at the problem, analyze each problem separately. We only have 2 minutes left, so here is the equation sheet you're going to have. Notice that this is kind of compact. The average velocity is delta x over delta t. Technically, this here is the velocity instantaneous, the derivative of x with respect to time. So the calculus people, I put that in there. It's technically not average. And likewise for acceleration, that's the instantaneous there. So INST. Work again. This equation here is superfluous because that is exactly the same equation as that. This here is also superfluous because that's the same equation as that. But I've put in all of your kinematic equations. Notice this equation and this equation are vector equations. The last one there is not a vector equation, but you can apply it to the components separately. It's not a vector equation because you can't have a vector v squared. You can't have velocity squared in some direction. Here's your definitions for trigonometry. So you can see how it's laid out in case there's confusion. I did say adjacent side A, hypotenuse H, so it should be clear. These things here, I had them in one of our slides, but I didn't get to them in the lecture. Those are useful laws. The law of sines will be useful as we get into forces. The law of sines says if I know like one angle in a triangle and two sides, I can find the rest of the triangle using this relationship. Sine A, the definition for this is, here's a triangle, here's angle A and side A, angle B and side B, angle C and side C. So the sides are opposite the angles. And then you just have that simple relationship between the sine of the angle and the side opposite it. This here should look actually really familiar. What does that look like? The thing I circle here in purple, the law of cosines. It looks like the Pythagorean theorem. The Pythagorean theorem is a special case of the law of cosines. When theta is 90 degrees, well, when angle C is 90 degrees, the Pythagorean theorem occurs. So the Pythagorean theorem is just the law of cosines. The law of cosines is more generally true. That's true for any triangle. So notice this is for all triangles. This here was only for right triangles. Okay, have a great day. I'll see some of you for class tomorrow, 11:30. The rest of you for the exam right here at 2.